Okay, so our next speaker is Michael Demidenko from Stanford University.
Hello, everyone. I'm your non-orthogonal speaker of the day. So I'll be focused on analytic workflows and modeling choices as it impacts activity in real data. I have no disclosures. So my talk is going to be a continuation of what Jeanette has covered briefly. So it's going to be focused on model estimation and biases. However, I'm going to focus a little bit more on the measurement and task fMRI side, particularly as it relates to the ABCD MID task with respect to the models two models we contrasted and associated behavioral differences and their implication for the estimates of bold activity and potential effects on the resulting measurements. So if you're sitting here thinking, I heard about ABC, MID, I don't care about either, hopefully I can give you a teaser of preliminary stuff with the HCP language task to illustrate a couple things as well. So to start off, measurement and task fMRI is both important as it is hard. So I'm not sure how many of you have experienced this, but maybe a week, month, a year after you fit some statistical model for your subjects, you heard a poster, saw a poster, heard a talk, read a paper, and you thought, oh crap, I may have messed something up. So we've all been there, but every modeling decision we make along the way, such as which regressors do we choose to build our models, which do we leave out, how do we account for some components that are too close, kind of how Jeanette mentioned we combine or drop them out, or which VIFs do we choose. All of these have implications for our subjects level models, which are our best estimate of the bold signal that is intended to represent our construct of interest. And these constructs are critical to our individual differences and group-related questions. So we often find ourselves in this kind of tug and pull between either combining or omitting regressors to avoid either construct contamination or some form of power loss. And so in our analysis, here's an illustration of real data for a single trial for a single subject. We compared two models. The first one up top being from ABCD, which fits effectively a Q impulse regressor in a feedback with their temporal derivatives. However, in our proposed model, we use a saturated model, here illustrating a sustained kind of duration response model for each of the components of the task. So there's Q, there's a fixation, feedback, and probe in RT here. And the saturated model becomes especially relevant when you pay attention to some of the timing information that you get from these subjects. So taking a look here at probe stimulus durations, which Jeanette briefly highlighted in her talk, and response time differences, focusing on the large win trial conditions, we see a distinguishing feature here. Specifically that the duration time is longer for hit trials, so people are successful during longer durations, as opposed to the missed trials. And there's also the inverse for response times, which is kind of expected. So there's this interaction that's occurring as a function of what participants are doing their scanner. So where do these things go? If we don't model them in our design, does the GLM genie solve it for us? So it's a short talk, but plain and simple in rapid event designs, what you don't account for in the models may pop up in adjacent estimates. So here illustrating the Q, single Q contrast, and a feedback one. Here we have the unthreshold map for Q feedback and our saturated model. So for the Q, things look a little bit more similar. When we do a pair difference statistical analysis, correcting cluster corrected and site adjusted, there's some increased activity in the saturated model, which may be bought from the kind of sustained duration model. The main difference that is especially relevant is potentially some of this unmodeled fixation and probe may be impacting some of these feedback contrasts, which I'll focus on more closely. So if we pay attention to this within condition contrast of $5 success versus a $5 failure, we find that contrast efficiencies between these models are effectively similar. So we aren't necessarily losing power. However, despite this, the activity is meaningfully more negative in the saturated model than our counterpart Q feedback model. And so if you pay attention here, you have increased activity in the Q feedback model, so you have higher subcortical, but the insular is less negative. So if we were seeing a power loss, we'd see things shrink to zero. However, we just see things slide down. So we can say that this is not attributed to something as power loss, and it's most likely, or in part, related to some bias that's stemming from the probe. So since the nucleus accumbens is a region of interest for this task, we can take a closer look and find that when you take the z-stat scores for each of the 500 subjects and take the difference between all scores between the two models, we find that consistently for the feedback contrast, the activity, the estimated activity for the nucleus accumbens goes down. So there is increased bias in our ROI and contrast of interest. And so what does this mean for our feedback estimates, particularly that contrast that we're estimating? So omitting probe and fixation has clear implications for feedback activity, and these activation estimates are likely inflated because some of these probe differences that appear both at a duration and a response. And there's risk for these the measured construct because they're contaminated by some of these adjacent components because they're so tightly fit in this design. So the saturated model, unlike the Q feedback model, can delineate some of these components, and I'll highlight one other more closely, particularly relating to the Q and fixation. And so traditionally, people either model the Q or feedback or fixation and feedback, and so they leave the other counterpart of Q fixation omitted. And for over 13, 14 years now, people have discussed that this anticipatory might be a motoric response because you're preparing for a response which might be distinct. And so we can really observe differences in patterns of activity in these cluster-corrected Q and fixation maps that we can estimate from the saturated model differently, whereby we find more visual, as we'd expect for a bright pink or yellow Q for a Q condition, and subcortical because of the reward or monitoring process. Whereas in fixation, you kind of get more of the sustained motor or dorsal striatal, which are related to more motor. So the question becomes, do we omit, do we lump, do we separate these out? In my opinion, I think modeling these components independently simplifies our interpretation and separates potentially distinct processes. And so if you are thinking, again, MID, so what? I'd like to give you an example from the HCP test, which we've been kind of working, and there are other tasks we've done as well. But the language is a nice example because it's kind of a rapid design, sequential components in the task for both language and math. So in each trial, you have a presentation, a question, and a response. So traditionally, these are modeled as math or story block regressors. So what we're effectively doing is there's this presentation, there's a story, and the question that we're lumping together, and they're computing our contrasts. So should we be doing that? Like the MID, I would argue, since it's a rapid design, that there should be an alternate model that should separate it and not lump it like it's done typically. And I present some of these contrast maps from both the traditional HCP style block model versus the alternate that separates them out, and kind of illustrate how we can get additional estimates of different components of the task. So we do find the activity maps for a story versus math HCP and an alternate presentation story versus math that are similar, but you do find that there's less of this negative activity. So part of this can be related because you get other components that are basically washing some of this out. And so in my conclusion and my position is there's really no free lunch in task fMRI analyses, and it's kind of important to take an approach where we build models that estimate parameters that represent both the cognitive process and our construct of interest. And we have to kind of highlight and remember that unmodeled components can sneak into adjacent components in these designs, and they don't just disappear. And so, whereas no model is perfect, we can iteratively build and improve our ways of estimating these parameters. So I want to thank collaborators, co-authors, and preprint, and if you are interested in end-to-end HCP pipeline, that's here. Thank you.
And maybe we have time for one quick question, if anybody has one. Yeah, Rasmus?
Yeah, I'll try to make it quick, but I was curious, in this design, maybe two related questions, but was there a jitter between the different, so you had the sort of Q fixation feedback, was there an additional gap in between there? And then if not, were these the only regressors that you modeled, or did the model also include some baseline regressors like a constant offset?
We didn't have a constant offset, no,
Okay.
and there is no jitter in the design for feedback in Q.
Okay.
No.
Yeah, just be cautioned because some software packages just implicitly add the constant baseline as a regressor, and in that case, you would have all sorts of multicollinearity issues.
Yeah, for sure, appreciate it.
Thanks.
Okay. I think we have to move on. Thank you very much.